In this video, we'll be looking at some basic ways to manipulate data in SPSS. Some of the procedures we'll be covering are general data cleaning, ways to recode data, ways to recalculate data, how to split a data file, how to identify outliers, and what to do with missing data. So to start off, data cleaning mostly refers to making sure that your database is accurate and complete. So most of the things you saw me do in the last video with labeling data, ensuring that it was coded properly, it had the correct decimal places, they were on the right scale, that could fall under data cleaning. So you're basically ensuring that the database you will be using is accurate and correct. The next step after you've made sure that your data has been cleaned and that everything is in order, you have to start looking if your data has any missing values. So this can be basically split into two ways in SPSS. So sometimes you might have missing values that are represented as dots. So this basically means that there was no value there. When you open the database or when you introduce the numbers, there was nothing to add there. So you just have a little dot. SPSS understands that this means there is no value there, although this person does exist. So I will treat it as a missing variable because that person might have data in the other columns, just not in this one. But then there's also something called user missing data. So this is basically you assign a particular number to missing data, and you can type this number whenever there actually is missing data so that SPSS knows that there is also nothing here. Now, why would you want to do this if SPSS already knows that the dot means there is no data there? Well, it's mostly because sometimes the database you would be using might be used by somebody else. So they don't know, or even you might not know in a few years when you open the same data set, if the number was just forgotten. So did you forget to input it? Did you skip over it? Or do you really not have any way of filling in that number? So in that case, it's better to have a user defined missing value that you can put in. And then the next time you look at the data, everybody can tell, oh, okay, there is literally nothing we can do in this scenario. We just have to treat it as missing data. And these are important because sometimes you might also use the same function of this user missing data to exclude data from your analysis. So for example, let's say you gave respondents the option of saying true, false, I don't know. You might not want to analyze the I don't know responses because you can't do anything with them in this scenario. So you just tell SPSS every time it sees I don't know, it should just discard that type of data. So these are options. Or you can also have, for example, ways of truncating data. So this means that you are not looking at specific values. So let's say you're looking at a reaction time test, and you might say anybody that took less than a particular value or over a particular value, let's say they were supposed to react very quickly, but they took 2 minutes to reply. In that case, you could say any value over 30 seconds, cut it out of the data. The reason why this is probably a better way of doing it than just going manually and deleting all of the data, one, because you might have a gigantic data set as you normally have in sociology, so it'd be impossible for you to do this, but realistically it's better because you're not deleting data. You're just telling SPSS don't use it this time. So it's always good to never delete data. That is not good practice. It might also be unethical. So it's always best to just code it in such a way that people know I'm not using it this time. Another useful manipulation is data recoding or transformation of data. So this is a common procedure that has to happen because the data that you've collected might not be on a particular scale that you are interested in, or it might not reflect the information that you actually want. So for example, this tool can be used to transform things like continuous data into categorical data. Let's say you counted people's age, but in reality, all you care are about individuals that are under a specific age or over a specific age. So then you can use this recoding procedure to basically tell SPSS, take values higher than this and lower than this and put them in this particular category. But more often what it is used for is, for example, when you collect a questionnaire data or psychometric questionnaire specifically, because sometimes the questions that they have are reverse coded. What this means is that although for, let's say, 9 out of the 10 questions, the values of 1 to 5 are accurate, and this is what you mean, you would sum them up to form a specific number, one of them has been reverse coded, meaning that the way the question was asked, the correct response, it should have been from 5 to 1. But because you can't do that, you just record what people actually gave you as a number. It's your job to take the 1 through 5 and reverse them so that SPSS knows how to actually handle this data. This is going to be a function that you might be using quite often, because sometimes you might not like how somebody else coded the data. It might not make sense. It might conflict with some of your other codes. So this is basically how you would go about fixing the data before you actually run any analyses. Now the second option to recode data, so the first one used the old versus new values. The second one is by using if statements. So what you are doing here is, as I mentioned initially in my example, you might sometimes want to group individuals or not use specific values that fall outside of a particular condition. So for instance, let's say you recorded lots of people in the park, but then because of ethics guidelines, you're not allowed to investigate anybody under the age of 18. So you might use the if statement, put age inside and say, if age is less than 18, select it. And basically what that would do is it would cut it out of that particular value, or in this case, put it in a separate category. So you have under 18 and then everybody else in your sample. So it's easier for you to select and know which cases you should be excluding. This is a very powerful tool that allows you to do all sorts of different manipulations. It's also a nice way to basically select outliers in case you need them, to make sure that you either keep them in your data set, exclude them, or treat them as a completely separate category. Recalculating is the method by which you either compute a completely new variable or transform the values in a specific variable to reflect the scale that you are interested in. So this is often done, for example, with data that is not normally distributed. You might perform different transformations on it, but you don't need to worry about that right now. What it's mostly used for is, for example, creating new values. So let's say I conducted a study in high school and I tested people on their English skills, reading skills, math, and writing, but all I care about is conducting a data analysis on the average score of every particular pupil in that class. So the way you would do it is you would compute a new variable that would take the mean of all of these other variables that you have in your data set and turn it into a single variable that you would use for your analysis. This is also the method that we will be using to look at Z-scores. So these are standardized values by which we can identify outliers, and it has a lot of useful features. For example, let's say you want to do a conversion from feet to meters or from frequencies into percentages. You have all of these arithmetic functions to be able to create data in the scale that you actually want to use for your analysis. So it's a very powerful tool. We'll be looking at this in the next few videos because it's very useful, and you should try to familiarize yourself with it as much as possible. Now, let's say you don't want to create new data, you just want to filter out specific cases within your current data because you figured out that you can't use them. So for example, let's say you've identified using the Z-scores that some values are classified as outliers. As I mentioned earlier, it's never good to delete data because you never know when you might use it, and it's also good for transparency and ethical considerations. So what you might decide to do is simply select specific cases and either not use them this time or highlight the ones that you would like to use. So the way you would do that is using the select case button over here. This window would pop up where you basically start to give it the conditions by which you are selecting data. So if you say if condition is satisfied, you would then input the values that you would say, if my values fall between these parameters, keep them. If not, take them out of the next analysis. So this is especially useful when you have things like Z-scores, and you would say if the value is between -3 and +3, so it's within the brackets that we find acceptable, keep it, and everything that falls outside of it would get that cut out icon next to them, so you know that they are not being used in your analyses. Splitting a data file can be useful when you are trying to conduct post hoc analyses. So let's say you looked at the main effect of gender and you found something significant, but you want to then be able to test each gender separately on a particular value, you would need to be able to split the data, so SPSS handles it individually. The way you would do this is by going to data and then split file and selecting the variable by which you want this to occur. Importantly, the variables can only be nominal or ordinal. So as I said, if you have a gender variable that is coded as 1 and 2, or you have something in terms of degree of study, and like we had last time, and then you put it in there, it will be a categorical variable that SPSS will understand needs to be used so that each section has a different output. Then you would only need to select if you want to compare groups. So this is the one over here, or organize output by groups. The only difference between these two is the table that it produces at the end. So if you use the compare groups option, you simply get one table where each subcategory is next to the other one. If you say organize output by groups, it just gives you 3 or 4 or how many separate tables for you to be able to copy into an assignment. But this is also important because once you've split a file, all the analyses you do will be done using the split file method. So if you decide that I only need it for one specific analysis, I'm done with it, you have to come all the way back here and then say analyze all cases and do not create groups. One important element before you can actually run any of your inferential statistics is to identify the possibility that your data contains outliers. So in brief, outliers are erroneous data that does not follow the general trend of other points of data you might have. Now, while the discussion on outliers is a bit complicated in terms of what should you do with them? Should you just cut them out? Should you try to incorporate them into a more complex analyses? These are topics that we don't have time to go into right now, but it's important for you to understand that many of the assumptions of the tests you want to run rely on the fact that there are no outliers in the data. So in this example, if you would include this outlier in these two continuous measures, you would see that the estimated trend line differs significantly and is a lot weaker than if the outlier was removed, because this seems to not reflect the general trend. This is a unique case that you might want to take out of your analyses. Now, the way you might do this is either by the use of Z-scores, so these are standardized scores of your data, which would indicate if something falls way above the standard deviation of your general data, or you might want to use box plots, which provide a graphical representation of your data in terms of the quartiles from the median to the upper and lower quartiles, minimum and maximum values, with outliers being outside of these parameters. So in this case, you would be able to see that normally distributed data should look like this, where the mean and median overlap, and they're kind of equidistant and has this nice symmetry to it. If your data contains outliers or skewness or any of that, you would see it here because this is no longer symmetrical around the median, and outliers would be identified as little dots. The differences in the techniques is that Z-scores are typically more powerful because this requires visual inspection and there's a lot of room for interpretation, but this can only be used with normally distributed data, while box plots can also be used with non-normally distributed data. So if you're really unsure on what to do, it's best to first look at box plots and see kind of what they identify. And then if your data is continuous, you can use Z-scores to see exactly how many values you should take out or keep in. A little note is that before you actually do any sort of outlier procedure, you must be mindful of any grouping variables that you're actually using. So it might not be beneficial to look for outliers before splitting based on particular grouping variables such as gender, because then your data would not look correct, and when you actually do analyze it, it won't follow the same pattern as the one you just remove the outliers from. So it's always good to remember any sort of stratification that you have in your data, implement it first, then look for outliers, and then conduct your tests. So as I just mentioned, Z-scores are a great way to identify outliers in your data. This is mostly because the tests you use rely on means and standard deviations. So the mean is the average of all of your data. If you have one random point that is way too high or way too low, it will skew the direction of your data. So you want to take that out. However, the question is which ones do you want to take out versus which ones you don't. And to reduce any sort of arbitration to this, the best way to do it is by using Z-scores. So in SPSS, what you would do is go to Analyze, Descriptive Statistics, and then Descriptives. You would add the scalar variables that you want to identify the Z-scores on, and you'd simply click this button that says Save Standardized Values as a variable. After you do this, you can ignore whatever output that comes out, because when you go back to the main SPSS window, you will see that you now have two new variables to look at, which are the Z-scores of your initial two measures. Now, the general rule for this is that any value here that is above 3 or below -3, you should consider as a potential outlier, and then use the select method that we spoke about earlier to identify them so they are no longer part of your analysis. The best way to normally do this without having to delete them is first conduct the analysis with the outliers, then say the process by which you identify the outliers, in this case Z-scores, and run a second analysis with the new cleaned data, and then to be able to compare the two. So your readers have an idea about what happened and how the change occurred after you've run the outlier procedure. For the second method of identifying outliers, box plots are pretty simple to create in SPSS. All you need to do is go to Graphs, Chart Builder, Box Plot, and then select Simple Box Plot. This window will appear. All you will do here is add the continuous variable that you want the box plot to be created on, and if you have some sort of grouping variable such as gender, you would put it on the x-axis, and then you'd basically click OK, and you would get some sort of output like this. So if your data, let's say, is normally distributed and has no outliers, it should kind of look like this. It's symmetric around the median, with the tails being kind of close to this, so there's no skewness, there is no issues or any outliers. While if your data does have outliers, they'll come up like this, where you have a value that SPSS has identified as a potential outlier that you would care about and you would want to investigate. So you see that even from this, you can kind of tell that the data doesn't seem symmetric, and it seems the data point 48 might have an issue. So you may want to go back to your data file and see what this 48 represents, and then try to identify why it might be an outlier. Is it because you introduced data incorrectly? Is it a value that does not make sense, or are they simply an individual that scored extremely high on an exam and they did very well? So this is why what you do with outliers is a contentious point, because even though it doesn't follow the rest of your data, that does not mean that this is not a valuable point of information. So it is up to you to decide what you would want to do with it. In this case, for your primary analysis, you would basically run it once with it included, and then again with it excluded, and mention the reason why you took it out. So now we're going to try to put some of those things in practice so we have an idea about how it would look like in SPSS on some dummy data. Okay, so now we're back in SPSS, where I will go over some of the procedures we just looked at in terms of how we process and look at data. So the first thing you would do in terms of data cleaning is look overall if any of these things don't match up. So some of the things are from last time, which we already coded and classified. But then we see that maybe some of the new ones don't really make a lot of sense. So these four values seem to be on the same scale, but this one seems to have 2 decimal places. That doesn't make sense. This one also has 2 decimal places. And then we see that this is ordinal, but this is scale. Clearly that's wrong. It should be on the same one because they seem to be measuring the same type of construct. All right, so that's basically how you would first handle this. You look at your data, you see kind of what's happening. The second is to look if there are any missing values. So there are ways to check if your data has missing values directly, but you can always eyeball it if you have one of these small ones. So for example, I can see that this column has not been filled in, but this I left on purpose because I will be editing this in a few minutes. And we see here that there seems to be a missing value. So this will be treated as a system missing value because there is nothing here. There never was anything here. It just seems to be a skipped data point. So if I look, for example, if I try to look at the frequencies of this one, you see that SPSS knows there is a missing data point. Now, the way you can treat this is either leave it as it is, or maybe tell SPSS that this is a missing data point and it's not just something you overlooked. This is also useful if you have collaborators and they might look at this data set and then they call you in the middle of the night saying, where's the data point for number 2? So the best way you do it is you go to variable view, you find the one that has a problem, and you mentioned here that there are missing values that you will treat as discrete. So in this case, the normal number is minus 999, which falls normally outside all parameters, especially for this one. And then what you would do is you'd come and label this minus 999. In this case, if we run the analysis again, we see that even though there's a 999, the system now understands this should be treated as missing. So that briefly covers the difference between a system missing and user missing data points. Now the next thing I'll go over is recoding data with new values. So in this fictitious experiment, I asked people 4 questions, one of which needs to be reverse coded. So my questions were, do you like pizza? And people had to answer from 1 to 5, I think, or 1 to 4. Let me see. Yeah, so they had to answer from 1 to 5, from strongly agree to strongly disagree. So this means that high values on any of these numbers means that people do like pizza, while lower numbers means they don't like pizza. So I had them rate them on if they like pizza, if they like chips, if they like working out, and if they like ice cream. Now, the reason why this is recoded is because a high value on this one does not mean the same thing as a high value here. This is introduced as a reverse coded question in my survey to make sure that people are just not responding with the same number on everything mindlessly without caring, but also because it's always good practice to sometimes phrase questions in a way that makes it more likely people will give you the correct answer instead of making it hard for them trying to decipher what it is you're looking for. But what this means in practice is that now we need to recode these values to reflect the actual scale that we want them to be on. So the way you would do this is you go to transform, recode into different variable, and I'm going to delete this because I already played with it for a bit. You have the likes working out. I'll give it a new variable called question 3 recoded, and then I will add some new variables. So I'm just going to remove all of this. Right, so what you would do is you start with the first value, and in this case on the scale from 1 to 5 you would have 1 through 5, but you actually want it to be the reverse. So if 1 is the highest on this one, you would need to put 5, and you do that for 2, 3 is 3, 4 is 2, and 5 is 1. Now you also have the option to input other things, such as if you knew that your data had missing values, you could put system missing with system missing. So in that case, it would add it and it will treat the missing data and recode it in the other one as missing as well. You could also give it a value. So for example, if we use this minus 999, you just put it as minus 999 and it would know that any system missing in the previous one are now relabeled as 999, and all you have to do is then change it in your variables so they actually reflect this. So we're going to be ignoring that for now. So if you click continue and OK, it did it. It's just going to be an output at the bottom. But basically now you see you have a new category that has simply reversed the number. So it was 1 here, now it's 5. As you can see, SPSS doesn't always put it correctly. So you would need to go here, look at it, say I don't want decimal places because they make no sense. And I would like this to be ordinal once more. You could also move the label over so it's easy for people to understand what it is you are actually doing. Okay. So now that we have all of these on the correct scale and they all reflect the values that we actually want them to do, we will be computing a new variable. The way you would go about this is to use the transform compute variable, and you could have something like fitness, and here you would take arithmetic, and let's see where the mean is. So you would select the all function. I don't know why in the 26 version it's not under arithmetic, but okay. And we put mean, double click it, and then you insert the variables that you want this to create a mean for. So you'd have the first question, the second question, and we skip the third one here because it hasn't been recoded here, and then we have the correct one. Okay, so when we clean this up, we click OK, it does some stuff. We look back at our metric, and now we have a fitness score, an average fitness score based on these four discrete measures. So these were ordinal, but when you turn it into an average score, you basically take the mean of all of these combined to take a single value. This is done particularly when you look at psychometric tests and you know that all of these individual questions correlate to a specific underlying construct, and you need to take either, let's say, the total or the average. In many scenarios, you would take the sum because that's the way you would add individual ordinal data, but for the sake of this example, I used it as an average. So this is the way you would compute a completely new variable using existing data. Another reason why you might want to compute a new variable is because there are frequency differences between your samples, so making any sort of statement based on a single variable doesn't make sense. So for example, let's say I recorded the number of Spotify memberships on each street, and if you would look by this, you would say that whatever is the first street has about 10, but this fourth street seems to have the highest number out of all of the streets that I recorded. But is this really a representative sample of how many people have Spotify memberships as a percentage of the population? If you are trying to estimate if people from smaller cities versus bigger cities, or in this case streets, have different preferences. Well, in that case, you would need to also look at the frequency of people living on that street. In that case, you would see that, for instance, although 23 seems to be the highest number, there are a lot more people on this street than there are here. So here you'd get 100% of people living on that street have a Spotify membership, while in this case only about 20 out of 80, so that's like 1 in 4, have a membership. So this is why it might be important to calculate the variable that better reflects what you're actually trying to understand from your data. So if you would want to do this, you simply go again to transform, compute variable, and in this case I would say something like membership per person, and I'll once again be using the mean value, but in this case you would be simply calculating as the division between two different areas. So you have number of subscriptions divided by the number of population. If you want to turn this into a percentage, you can just simply have some brackets around and then use the multiplication operator, 100. Okay, let's see what it did. So it said it did some things. Let's see what the output looks like. It created a new variable called the memberships per person, and you find what we expected, that on the first street there's actually 100% membership, while for the other ones it's lower. So realistically, the first one, even though it had this 10 compared to this 23 or 13, had the highest number of memberships per person. Okay, so now we're going to continue with looking at outliers. The first method that I'm going to show you are box plots. So let's say I have a continuous variable that in this case was number of coffees per day, which is discrete because it allowed me to count how many coffees somebody said they drank in a day. So as you can kind of see, there's ranges from 2, 1, 0, maybe some people drank 3, some extremes drank 4, but then there's this value that clearly in this database seems extreme, 50 coffees. It's probably a typo, maybe there's a mistake, or the person probably died in the meantime. But what's important is for us to determine statistically if this is indeed an outlier and then what to do with it. So imagine that you actually had a database that spanned a couple thousand of these rows. It would be impossible to maybe pick out this exact number and see that there's a problem. So the best way to do it is first looking at box plots. So this is where you go to graphs, chart builder, click OK, and then you basically go here until you find the thing that says box plots. Since you only have one variable and nothing that is splitting it, you pick the simplest one, and then you go and select, in my case is the coffee per day. You put it on the y-axis, and that's basically it. That's all you need to do. It shows you a little preview, but this is not an accurate preview. This is basically just SPSS's preview. Click OK. It might take a while for it to do something, and then it spits out this thing, which if you look at it here does seem symmetric. So there is the data does seem to be split in a rather normal distributed way, but there's clearly an outlier over here that is at the 50 mark. So it identified this as a potential outlier, and it's saying that it's the 90th point. So if I go back into my data and check the 19th row, and then scroll to this person, I find this number. So SPSS using Boxplot says this might be a problematic number and you might want to take it out of your analysis. So I'm going to do that now. Let's say I replace this with, say, a 5, or I just delete it completely. Let's do that, it's probably better. I run the analysis again. These should stay in the same place. And bam, this looks a lot cleaner, and this is what you would expect if your data is normally distributed. So this is kind of your expectation. So it shows that just taking out one outlier can greatly improve your data, and now you can actually do something with it. However, let's say that's not the method you want to go by. Let's say you're disputing with a colleague if it's okay to delete that simply based on the visual inspection. The other way to do it is by looking at the Z-scores of this distribution and see if there are any differences that would indicate this is indeed an outlier. This in itself is quite easy to do. All you need to do is go over to Analyze, Descriptive Statistics, Descriptives, then put the variable you care about here and click this Save Standardized Values as a different variable. You click OK. You don't really care about this one because you know it's already biased and it's not that informative. And now you see it's given you this nice list of values. Now we can clean this up a bit because it gave me too many decimal places. I only care about 2, let's say. So I go back, this looks a bit better. And as you remember from the slides, the cutoff criteria is 3. So if I go down this list, everything seems fine except for this one, which seems to be way over 3. So it'll be classified as a potential outlier. So let's say now you're kind of sure that this is an outlier. What's the best way to handle it? As I mentioned, deleting it is never the right answer because you have no idea why this data exists, why it might be useful in the future to have. Maybe somebody else will collect more data and you'll find that it's not just one outlier, it's actually a group of people that behave this way, and your data was not distributed properly. So it might be bimodal, where some people drink excessive amounts of coffee, some people drink a little coffee, or maybe the way you quantified coffee is different. So what you would do here is you go to select cases and you would say if condition satisfies, and then you would do this. You take the Z-scores that you just have and you would say if this is bigger than and then you put the arithmetic absolute 3. So this basically means that if it's bigger than +3 or bigger than -3, it's an easier way of writing it instead of writing out the whole thing, which I find is more problematic because you might make mistakes. Click OK. It did some stuff, and when you look back, now it's incorporated all of the incorrect. Okay, so that shows why you actually need to write the formula in such a way that it knows to keep those values. So it excludes these ones, so now this should work. Okay, yeah. So by putting it that way, you're basically saying everything that falls within that range, I'm fine with, please keep it. If not, then exclude it. So now we left the value here, but it shows SPSS that we don't want these to be included into our analyses. We want to treat them as non-existent for the sake of our current experiment. Now for the final part, we'll be looking at the split file function. This is, again, it's mostly if you want to run analyses that require a separation of the file. You don't do anything that's complicated at this particular time, but it's just because going to use it as an example. So let's say you wanted to look at fitness levels, but you wanted to compare the means and standard deviations in a table between males and females instead of just looking at fitness overall. So the way you could do this is by splitting the file so that it understands to use the gender variable, which is over here. So this is a nominal variable coded as ones and twos, and you want it to separate these values based on that. So this is easily done. You go to data, split file, and then you say organize output by groups. I think this is best because it will give you two tables, one for male, one for female. So you tell it, please do this by gender. So it did it. It says, it gives you some output saying they split the file, but this did nothing to your data. It doesn't show anything here that's of value. You might have a variable at the end that shows that, but most of the times it's just something SPSS understands you want. So now if you go to say analyze descriptives and you add in the variable we care about, so in this case it would be fitness. Boom, it created two tables, one for female and one for male. So it's easier for you to kind of understand how the means and distributions differ between the two. Now, because you split the file, SPSS is going to use that split file for absolutely everything until you go back here and tell it to stop doing that. Just take it out and say analyze all of it together. SPSS will say split file off, and that's basically it. So these are the kind of the basic operations that you need to get used to because you will use them pretty often when you're given large data sets. So it's best to combine these with the previous video and what I mentioned the first part of this video and see what you understand, what you can try out at home. Nothing bad is going to happen if you just make up some data and see if you can follow along.